Now this is two types of problems inside of pH effect. Given an hydroxide, we worked one a little bit ago, an aluminum hydroxide, okay, where you determine solubility of that hydroxide salt. And you have many transition metal hydroxides. Iron 3 hydroxide. And it has a KSP (2.5 times 10 to the minus 39). So this is a 1 to 3 ionization, so that'd be a fourth root of KSP over 27. So iron hydroxide goes into solution to generate iron 3 plus 3 OH ions like that. Problems will say, what's the pH of this solution? Well, if you get the OH, you ought to be able to get the pH. Okay, so at equilibrium, this is an X and 3X, and solubility is the fourth root of KSP over 27. Set up your, like we did at the beginning of the lecture, in writing out what the KSP expressions are, and solve for X, which is the solubility. And so that's the fourth root of 2.5 times 10 to the minus 39 over 27 moles per liter. And so that is 2.59 times 10 to the minus 39 divided by 27 equals fourth root. And I get, hit a wrong button. Hang on. The solubility is this. Well, the solubility is the iron concentration if the problem asks you for the iron concentration. But the hydroxide ion concentration is 3X, which is 3 times the solubility. (2.94 times 10 minus 10). And POH, therefore, is minus log of that. We get 9.53. And then pH is 14 minus that 9.53, 4.47. So there's your pH. Some of these, even though they're listing as hydroxides, do not come out as having pHs above 7. They are actually acidic in their nature. The other type of pH effect is how do you increase solubility of a salt in solution. And this is increasing salt solubility using acidic solution. This only works with salts that, if you add an acid to it, will inherently form a weak acid in itself. For example, you have salts like calcium sulfite and magnesium sulfite or sulfate. These are salts that build up, and they're called scale, mineral scale. and they ruin elements in your water heaters and Mr. Coffees and what have you, and especially in high salt water areas, it'll build up. Now, if we take, either one of them, take magnesium salts, and it ionizes into a magnesium +2 plus an SO4 2-. Now, if I place an acid into solution, it delivers hydronium ions into solution. Now, this could be a strong acid or a weak acid, vinegar to nitric acid, whatever you want to use, but as long as it delivers hydronium ions. Well, this is such a strong conjugate base, it's going to absorb that positive hydrogen and make an HSO4 -1. This is a weak acid. It's the conjugate base of the first ionization step in H2SO4. You remember the H2SO4 is a strong acid only in the first ionization step, but the second ionization step, which comes off of this HSO4, is a weak acid. Now, what happens is this is assumed to be removed from the system. It removes the SO4 2- from the equilibrium. That is the SO4, let me do it this way. You have magnesium sulfate going in, delivering magnesium ions and sulfate ions 2-. Put that on a sea salt right there. Then if you put an H in there, what it's going to do is combine with the sulfate and give you HSO4-. Well, this is removing the SO4 by that combination. It removes that SO4 here, so what do you have? This is gone now, so it tilts like this and shifts to the right, delivering more magnesium ions into solution. And see, that's missing. And then it shifts right, which is increasing solubility. So you have to have this one, I have to have an acid. When you put this acid in, it removes one of the product side, tilts left, shifts right. And therefore you establish a new equilibrium, which is less salt in the system. So many people will pour just regular cleaning vinegar down in their Mr. Coffee to dissolve out the salt scales on the thermocouples, heater coupled or whatever it is, in those appliances. So that's essentially what it is. So on a test day, when you see which of the following will increase the solubility of the salt, whatever the compound they give you, it's always that strong acid will do it, because it delivers the hydrogen, which turns part of that salt into a weak acid and causes the reaction to shift more salt into solution. If it doesn't form a weak acid, it's not going to increase the solubility. I'm trying to think of one. Silver chloride, for example, goes to silver ions and chloride ions. Well, putting an acid in with a chloride goes to HCl. Well, that's not going to happen. The conjugate base, or the anion over here, must react with the hydrogen that you add to form a weak acid over here. And if it doesn't, you don't increase solubility of the salt in that particular case. All right, let's see what's next. Okay, let's take 10. No, that's 15. If you need to take a break, take a break. Okay, I'm going to push through this because it's going to take me the rest of the time to get through these two. Okay, so I'm going to move on. Common ion effect. Just as in the acid-base equilibria, common ion functions to reduce extent of reaction. In this case, of course, it'll reduce solubility. The salt. So this functions to reduce solubility. So if we had AgCl and it ionizes to silver ions and chloride ions with a KSP to equal 1.8 times 10 to the minus 10. This in pure water, the solubility is simply the square root of the KSP. It's a 1-to-1 ionization. And so that's the square root of 1.8 times 10 to the minus 10 molar. 1.34. Yeah. 1.34 times 10 to the minus 5 molar delivered into solution. Now, if in presence of common ion, say you put a certain concentration, a very light concentration of hydrochloric acid in, well, it's going to deliver chloride into solution. In present common ion, assume Cl minus from, say, HCl or some other salt or whatever, is 0.010 molar in solution. Then you drop your salt in there, your silver chloride in. Well, what's the solubility under those circumstances? Well, number one, you can't use the square root formulas or cube root or fourth root or whatever. You have to use the ice table because one of the products is already present in the initial row. See, you had no silver, and whatever you've determined to be silver will be the solubility. But you already have 0.10 molar in chloride to start the problem. Change in concentration will be plus X plus X. Well, it's going to be smaller than if you were in pure water, so you can drop X on this end. But the X is what tells us how much of the silver chloride goes into solution. 0.01 plus X, which is 0.01 molar, because you can drop that in this one. So, setting up your KSP expression now, I'll try to keep that on the board up here. KSP will be silver ion, chloride ions, a 1-to-1. And so that would be X times 0.01, and that's equal to 1.8 times 10 to the minus 10. And so solving for X, which is the solubility of AgCl with common ion, is 1.8 times 10 to the minus 10 divided by 10 to the minus 1, and that'll give you 1.8 times 10 to the minus 9 molar. There's your solubility with the common ion. Here's your solubility up here with the in pure water. So it went from a 10 to the minus 5 to a 10 to the minus 9 solubility when you put that common ion in there. So it's a big drop by 4 orders of magnitude in this concentration. So that goes from 10 to the minus 9 with common ion versus 1.34 times 10 to the minus 5 molar in pure water. So you can see the major change in concentration. Okay. Any questions? We'll work some problems here in a few minutes. Last topic in our chapter is complex ion equilibrium. The complex ion equilibrium functions to increase the solubility of a salt. By combining with a complexing agent. Complexing agents are substances which readily react with one of the ions of the salt and forms a compound that removes that ion from the equilibrium expression or equilibrium equation. Here are some complexing agents. Like silver will combine with a cyanide, and silver also with, if you bubbled ammonia through it, forms an ammonium ion. It'll readily combine. Look at the size of the K values over here. These are called KF expressions. Kf is the equilibrium formation constant. So the formation is all positives in these cases. Look at 10 to the 18th. 1.7 times 10 to the 7th is the formation constant for silver ammonia complex. Well, something with that large a K value will take every bit of the silver out of the system. And so so more of the silver, whatever, salt will keep dissolving and sending more to replace what is taken out by this. These are essentially removed from the equilibrium of the salt and salt ions. So this is what we use: the silver, chloride, and ammonia. So let's say we're given. Oh yeah. Where's my negative here? Just go back. That went the wrong way. There we go. Thank you. Let's say given silver chloride in an NH3 solution. Okay. So if we take silver chloride, it will, of course, ionize into silver ions and chloride ions, and we find that its KSP is 1.8 times 10 to the minus 10. Now, in this complex ion equilibria section, you have to use two equations. one for the salt ionization and 2 for the complex formation. Well, the complex that we just showed you was silver and ammonium. So we have silver in solution plus NH3, which is the ammonium hydroxide, but ammonia converts to the ammonium ion in solution. And this presence of this ammonia, big time, goes to silver amine complex. Let's see if it's NH4. No, it's NH3 2 plus. This is a silver amine complex. Is what it's called. Now you'll be given the complexing agent, so you'll know exactly what hooks up with the what ion. So this formation is a Kf expression, which is 1.7 times 10 to the positive 7th value. And so when you add these two together, you can cancel out your silver, and the net equation, actually this is 2 because this is 2. When net equation is silver chloride in the solid salt plus 2 NH3s in equilibrium with the silver amine complex plus chloride ion. Now the K net is a result of adding two equations. And if you recall from the equilibrium on gas phase in 12, chapter 14, when you add two equations together, the equilibrium constant of the net is the product of the K values. So K net in this expression, well, I'll put it over here. Well, K net is equal to KSP times the K of formation. And in this case, 1.8 times 10 to the minus 10, and 1.7 times 10 to the positive 7. So that is 3.1 times 10 to the minus 3. Big jump from 10 to the minus 10 to 10 to the minus 3. The issue is a couple of issues. This is a larger value, meaning that this is increasing solubility significantly. Anyway, in the analysis, you will have to use this equation because the amount of chloride delivered into solution is the new solubility here. So we're going to set that up and show you how that plays out in a given calculation of increased solubilities. But what happens here, because of the size of this number, you cannot drop X in the calculation sequence. You have to use quadratics or polynomial solutions. If you look at some of the K formation, there you got nickel complexes with 6 ammonias. And so you got a polynomial in the 6th power you have to work with. And they have computers that break all of that down. But you'll only see something with a square or something that's easy enough like this. I'll show you. But anyway, the reaction of the complexing agent with the salt is this equation. We'll just bring it down here. And we're looking for this, and this K net is 0.0031. Okay, and with this, you set up the ice table, just like we have in the past, because you're analyzing for solubility, and we're looking for this chloride here. And in each case, remember, we never consider the salt in this context, but we can consider the ammonia. Say you send in, start with 0.10 molar in the ammonia. That's what you put in the system to shift the equilibrium. Well, this is 0 and 0, and then it's minus 2x, x, and x, which gives you a 0.10 minus 2x, x, and x. But you cannot drop the 2x in here because of the size of the equilibrium constant in this particular one. So you set up the K net is products over reactants excluding the salt, so that would be the silveramine complex times the chloride divided by the ammonia, NH3, and that one has to be squared this time because it is included in the equilibrium expression. Substituting the CEQ, that gives you x squared over 0.10 minus 2x, and that has to be squared in the denominator, and that's equal to 0.0031. And so we're trying to solve for x right here. Well, if you see this, I know you're probably a step behind on this, writing and scribbling and listening. Take square root of both sides and makes it in a linear form, and so I'm keeping it in simple mode type problem so you can see how this thing works out. So we can take so check that before you check any other, start running off to the quadratics real quick. And so it'll simplify it like this. So you have x squared over 0.10 minus 2x squared is equal to 0.0031, and of course that will simplify to x squared, x over 0.10 minus 2x equals 0.0031. Now you're a rather simple algebra problem now. Solving for x.
Would it still be 0.0031 if you take the square root of both sides?
3-1, yeah. Oh, yeah, you got to take the square root of both sides. That's what I said, wasn't it?
Yeah.
Duh. Okay, so, yeah, let me straighten that out. Thank you, dear.
Okay.
0.056, yeah. 0.56. Now solve for it, yeah. So we have x on to 0.056 and 0.10 minus 2x. X equals 0.0056 minus times 2 0.111, and you can't have a negative like that. Wait a minute. Did I misfire? Yes, I didn't put enough in. Solving for x on both sides, that's right. That's right. As far as the math goes, that's right. But you can't come out with a negative. So, all right. So there's your new solubility thing. Anyway, let's see where it goes. 0.0056 divided by 1.111. And so you have a solubility of 0.005 molar solubility with NH3 complex. So, going back and look at, for a second. So you can see there's a major change in these, increase in the solubility right here, provided you know how to do algebra. Anyway, so 1761, I think is the second half of that question. Okay. You've got silver bromide going to silver ions, and then the bromide ions, and the KSP is given to be 5 times 10 to the minus 13. Then you react that with ammonia, gives you the silver amine complex again, plus, and the K formation is 1.7 times 10 to the positive 7. Add those together, silver drops out, you have this silver bromide plus 2NH3 and silver amine complex plus the bromide ion, which will be a solubility, and then KSP times KF equals 5 times 10 to the minus 13 times 1.7 times 10 to the positive 7. Well, that's still a small number. I'm going to double check. Yeah. So it goes to 8.5 times 10 to the minus 6. Still didn't get a bigger, very big number, but still is significantly bigger than a 10 to the minus 13. Well, using this as our equilibrium expression, equilibrium equation, then equilibrium, ignore the salt, you have 2x, x, and x like that. So your K net now is the product AgNH3 2 negative bromide over the ammonia. Same as we did before. This would be, we'd have to have a, did I give ammonia amount in? 1 molar, yeah. So this would have to be 1 minus 2x right there for the equilibrium, because I start with 1 molar. And so you use up 2x of it. So that's x squared over 1 minus 2x. And that's got to be squared, and that's 8.5 times 10 to the minus 6. Take the square root of both sides, and we have now x 1 minus 2x to equal 2.91 times 10.92 minus 3. And so move that up here. I'm going to put it in fractions. this is the same process that we just did. Reciprocal times 0029. And so that is new solubility. And that after the complexing agent is added into that. So I've covered all of the major topics and problem types that you'll run into for the exam tomorrow. I'll have it set up for you and ready to go. Be sure you stay in that practice exam I sent to you. Be sure you can handle those, and you'll do fine.